This session actually is not really about black holes. I'm sorry. This is about how not to destroy data. Well, have a good day. But thank you all for sticking around, bearing through the weather to hang out with me for a little bit. My name is Michael L. Perry. I work at Improving, just like Craig, if you were here for the last one. I'm from the Dallas office, as opposed to Craig, who's a bit more local. So there's my email address, and there's also up there a link to a previous recording of this talk. But please don't get up and go home just to watch that video, because this one will be different. I don't know yet, but I will not destroy that information once we have it. In fact, I believe that the slides and audio are being recorded for this one, so we'll see if they make it out online. And also, I am a Pluralsight author. I've got a couple of 30-day subscription cards up here, and I give these out for good questions. I really like good interaction during my talks. So, let's talk about how not to destroy data. How many people write systems? All right, quite a few hands. Excellent. That's just to keep you energized. All right, how many people write systems using these 4 operations? Create, read, update, delete. Right. We write a lot of CRUD systems, and in fact, you can one-to-one map these 4 operations to these 4 operations inside of a SQL database. Now, the question is, which of these operations destroy data? All right, who thinks delete destroys data? All right, delete destroys data. So if we want to write a system that doesn't destroy data, maybe we should not use delete. In fact, I like to give it a different term. Rather than delete, I want to make sure that you know specifically what you're doing. And so I like to call it purge. So you are purging data from the system. So how many people write systems that have no delete statements in the database? Still have a few. Still have a few. All right. Is there another operation up here that destroys data? Update. Yes. Update destroys data because I should probably turn off notifications. I hope that wasn't embarrassing. I didn't see what it was. But it looks like Slack. Don't look. All right. So yeah, update replaces the data that was there. And so update sounds so friendly. I mean, you're just refreshing some data. It was out of date. Now it's up to date. But I like to give it a different name. Let's call it, switch back. Let's call it alter. All right, so we are altering the data that is in the database. So now I think we have a much better acronym for the kind of systems that use insert, select, update, and delete. It really tells us what we're actually doing. So what if we want to create a system that doesn't ever destroy any data? So we don't want any updates, we don't want any deletes. How can we do it? Well, we have some options. So let's take a look at those options now. We're going to fly to the different worlds and check out our different options for the salvation of humanity. And so one of those options is that we can use an audit log. An audit log would look something like this. We've got our speaker table, we've got our session table. This would be a database similar to what is running this conference here. And so we've got Caleb Jenkins in the speaker table. Then he's got a session, so you've got a foreign key to that speaker. Unit testing in all those hard-to-reach places. So we'll capture a few more Craig stunts. Before this one, he did a session on secure applications by design. And then here's me with, of course, the session that I proposed, black holes are cool. But now we're going to make some changes to this database. And so as we make some changes to the data in the database, we want to keep an audit log of all the things that have changed. So let's go ahead and I like to spell my name with my middle initial. That way I'm not confused for the author as I was recently on Twitter. So let's change Michael Perry to Michael L. Perry. And so now we can see the speaker ID number 3. We made this change from this value to this value. Sound good? Okay, so we're keeping that audit log. And then Caleb decided to be a little bit more clickbaity with his title, so we changed it to Coding Naked, unit testing all those hard to reach places. So session 12 changed from this value to this value. That's all great. And then I learned this is actually a software conference, so I changed the title to How Not to Destroy Data. And so we've captured all these different changes to our data inside of this audit log. And now I can go through this and I can see all of the history. I can preserve all of that data. So does anyone see any problems with the audit log that we've created here? It's going to get really big? Yeah? Okay, yeah, I didn't record which column, who did it, or when. Yeah, that's probably that's something that you could add pretty easily to the audit log. It is not strongly typed, exactly. So a speaker name, we might reserve maybe 100 characters for a speaker name, but a session title, maybe 300 characters. So what's the data type of the audit log? And now what if we're changing an integer? What if we're changing a bit? We have to turn those into strings. So it gets really wonky, and you've got loose typing, and you have to just reserve as much space as the largest column. So it's got some problems, but in summary, audit log, simple, really simple. This is a great check mark, but not type safe, and it is also not reliable. What do I mean by that? So I could change the data, but forget to write to the audit log. So now, can I really trust that the audit log is complete? Well, I have to know that my code was correct before I could trust it. So I'm not truly relying upon the audit log in order to know the current state of the system. Therefore, it's not reliable. Excuse me. So for the type safety, thank you very much. So let's take a look at another option. All right, so this is called event sourcing. How many people have heard of event sourcing? Had quite a few, excellent. So in event sourcing, we are going to keep track of a history of events. We're going to go ahead and stream those events and keep them in a centralized data store. So one event that happened at some point in time is the speaker was created with the speaker ID 3 and the name Michael Perry. And then later on, a session was created for a different speaker, speaker ID 1, and we gave this the session ID 12, unit testing all those hard to reach places. And then some point later, the speaker name was changed. So here's speaker ID 3. Okay, so that relates to that earlier object there, and the name was changed to Michael L. Perry. And so if I want to figure out the current name of speaker number 3, I could just go through this event stream, and I could create an object with speaker ID 3 and play all the events against that object. Most of the events it doesn't care about. I'm not a session, so I don't care about session created. I'm not speaker ID 7, so I don't care about that message. Oh, here's speaker ID 3. Let's go ahead and play that against the object. And then we've got a full rehydrated snapshot of the current state from the history. So let's capture a few more. We've got a couple of sessions that were created. And so here we are capturing this entire stream of history of changes that have occurred throughout time, and then rehydrating the current state of the system whenever we need it. So comparing this to audit log, I would say event sourcing, not simple, but it definitely solves the type safety and the reliability problem. So it's type safe because each of these events has a defined type. And what we're storing in an event stream, typically we don't store that in a relational database. We typically store that in a specialized type of data structure called an event store. And so it captures the actual type of the event, and it is reliable because we are relying upon it whenever we want to know the current state of the system. So it looks like we've solved our problems. We've sacrificed simplicity, but sometimes you have to give up simplicity in order to get something more. But let's take a look back at our event stream and see if we can find any other areas that we could possibly improve. So let's go ahead and create another event that the session title has changed. So I'm going to change the session title for session ID 18 from black holes are cool to the information paradox. So now let's talk specifically about Stephen Hawking. Oh, wait a minute. No, it was a software conference after all. So, okay, session title for session ID 18 changed to how not to destroy data. So, what's the actual current title of this session? Well, good. I'm glad you were reading the schedule to get here. Awesome. And you can also tell that from the history. You can see that's the last one. So if I play them in order, that's the value that I end up with. But what would happen if they were in the opposite order? And you would end up with the wrong title. So these two are order dependent. The information paradox has to have happened before how not to destroy data. And we're capturing that by this timestamp, so it seems like everything's okay. So those things are order dependent. But let's take a look at these. So the speaker name is changed. That's related to speaker ID 3. Session created, also related to speaker ID 3. So they are both related to the same object. And we can see that that object was created up there at the top. But are they order dependent with each other? No? No, I can change the speaker name or I can create the session. Neither one's going to depend upon the other. So those two are not order dependent with each other. What about with that first event, the speaker created? Yes, absolutely. You have to have created the speaker before you can change the name or create a session. So sometimes order matters, sometimes it doesn't. So in this case, order matters because we're changing the same property. In these cases, order matters because we have to have created something before we can change it. But in a lot of cases, order doesn't matter. Yet, the event stream always encodes that timestamp. It always puts things in a full order. So even when order doesn't matter, order is imposed. It might not seem like such a big deal, but as we start looking at different architectures, we'll find actually there are some real advantages to things that don't have a defined order. For example, if we're using queues. I send a message, I put a message on a queue. Sometimes your queuing infrastructure does not guarantee the order of delivery. If it does guarantee order of delivery, then it has to go through a lot of extra work in order to give you that guarantee. So if you can live without that guaranteed order of delivery, then you can be more scalable, just as one example. So event sourcing is not partially ordered. In fact, neither is Audit Log, because you've got that linear history. Everything comes in a particular sequence. Let's talk about a third option, one that is partially ordered. And this is one that I call historical modeling. So it is not simple. So the rest of this is not going to be a big cakewalk. But it is type safe, it is reliable, and it is partially ordered. So let's take a look at our first example. Historical modeling. It's like space-time bending around objects based on your perspective. It's actually not a bad metaphor. So let's start with the speaker table. So this is the way that we might represent a speaker in our system. So we've got a speaker ID, that's our primary key. We've got a username, that's going to be a unique kind column, so we'll put a uniqueness constraint on it so that we can look up the speaker. And then we've got the speaker's name. So what problem do we have with this so far? What's that? Two primary keys? Actually, that's going to be part of the solution, but but the problem that we're seeing so far is that name is mutable, and we don't want any updates. So if we have a mutable property in here, I'd have to update it. So let's go ahead and take name out. And now we've just got our speaker ID and our username. And so that name had to have gone somewhere. We'll come back to where the name went. But the identity of this speaker, we'll say, is the username, not the user ID. We want the identity of all of our objects to be something that we knew about it before we even created it. So the database is just creating this surrogate key that stands for the object. We want to have some identity independent of that surrogate key. And that's going to help us a lot with our asynchrony in our architecture. So, so that way, I can create a speaker and just pass in a username, and it creates it. I don't have to wait for it to have been created before I can get back. What was the ID, by the way? And OK, now that's the identity. So now I can create the thing and asynchronously just send it off. So that's going to help us. So now I've got my speaker identified by username. When I want to talk about that speaker through my API, I can always say the speaker with the username Michael L. Perry. And that is the object's identity. So I'm never using the surrogate key outside of the system. I'm only using that identity, an identity that I knew ahead of time. That's going to help us. All right, so let's talk about the sessions. So we've got sessions that belong to speakers. So we've got our, oh goodness, that's still chatting. All right, we've got our sessions that are talking about speakers, or that belong to speakers. And we shut down Slack. There we go. There we go. Yes.
So your code
Mm-hmm.
name, because you said it was beautiful.
Yes.
But username can be changed.
Okay, good question. So I removed name because it's mutable, but what about username? Couldn't you change your username? We're going to make the assumption that in this system, once you've registered for an account, you can't change your username. So, but yeah, if you do need to be able to change it, then you need a model for that. Yes? Right, exactly, exactly. So, for the question, thank you very much. Usernames, yes, usernames should be unique as well. So yeah, that's why we've got that uniqueness constraints there. But names themselves don't need to be unique. Yes. They would make a very good key, yes. And in a different example, I use them for exactly that purpose. So we will see that. OK, so we've got our sessions. Title is mutable, so let's get that thing out of there for right now. That's going to go somewhere else. And instead, I want to add a timestamp. Let me tell you the reason why. The identity of the session, if I didn't have the timestamp, would just be the speaker ID. Because remember, we don't want the surrogate key to be the identity. We just want that to be what the database uses. So that means from the outside, if I were to talk about a session, I could only talk about one session for a speaker. I want speakers to be able to have multiple sessions. So I'm going to create some uniqueifier, some additional thing that stands in for identity. And so there, I'm going to use a timestamp. So you see here, we've got two examples already of uniqueifiers. something that the user provided, the user name when they logged in. Yes, so session ID and speaker ID would be unique. The problem is that they are surrogate keys, so that I don't know them until after I've performed the insert. So I want to be able to identify something by some values that I don't yet know before I've done the insert. So I'll provide a timestamp. So that means as a speaker, I'm adding some sessions, and every time I add a session, my browser just captures the current time, sets it as a timestamp, and sends that on its way. And now my browser knows the full identity of the session before it even gets to the server. So that's how we're going to identify our sessions. And so that means that I can now put uniqueness constraints on that pair of columns. The speaker ID timestamp pair is unique, and that uniquely identifies a session. And that means that my API now can use the timestamp, but not the speaker ID, since that's an internal, that's a surrogate key, but the username. That combination identifies the session, and so a session through the API looks like this. So it is the session with the speaker that has the username Michael L. Perry and the timestamp of 2017-18-17. Yes, exactly. You would have to do a lookup first to find the speaker ID. So you look up the speaker by this identity here, and then once you've got that speaker ID, you can do the insert. Yeah, so not simple, but this is giving us a few advantages. We're only doing inserts, and we are inserting based on identities that we have outside of the system before we've even sent the message to the server. So this is giving us our first set of rules. Our first set of rules are the rules around identity, that every field is immutable. You never update, and you never delete. Surrogate keys are only used internally. The identity of the object is everything besides the surrogate keys. Question? How do we handle uniqueness? So far we've seen uniqueness constraints on all of the fields except for the surrogate key. So going back here, we've got a uniqueness constraint on the first table of just the username, since that's the only other column. But on the second table, a uniqueness constraint that combines the other two columns. Right, you can only have one speaker with a given username. And then each of the sessions have to have a unique timestamp. Yes? Mm-hmm. Could you also use the username? I prefer not to, because the username would be a string as opposed to an integer, and so it would just be putting more work on the database. So you would store the entire username as opposed to storing just the integer key. Yeah, okay. Okay, so let's get a little bit more complicated here. Let's say that I'm filling out my my submissions. I add a few sessions, and I accidentally added a session I didn't want to. So I need to be able to delete these sessions. So what's a good way to delete if I don't want to actually delete any records? Yeah, we can use a flag here, mark it deleted. But that's mutable, right? Yeah, we don't want anything that's mutable. So this would just be turning a delete into an update. Still not what we want. Yeah. Mm-hmm. Excellent. Perfect. That's exactly what we're going to do. We're going to insert into another table the deletion of the session. So that's got the foreign key back to the session that we're deleting. And so now we can uniquely identify the deletion by its session ID, the thing that it's deleting. So we're just inserting. And now we can do that query to figure out which sessions are still there. Yes? How do you undelete? That is a very good question. So let's suppose that I wanted to undelete this thing. So I said, OK, let's have another table. That is the session restoration table. OK. This might start to get kind of crazy. So I go ahead. OK, here's session restoration, points back to session deletion. Oh, wait a minute. No, I really did want to delete it. So I wanted to insert another session deletion. But the session deletion is unique by the session ID. So I can't insert another one. So that means I have to have some way to distinguish between deletions. Well, that would just go on forever. So we could create a new instance of the session. In fact, in some models, that's what I choose to do. When there's a lot of data associated with it, as there will be with sessions, that just puts an extra burden on the end user. So, so yeah, here is the query that we were talking about for seeing all of the non-deleted sessions. But what we're talking about now is, what if I need to have an additional uniqueifier for the deletion, so that then I can identify a deletion by its session ID and its timestamp. And so in order to talk about a deletion from outside the system, I'd say, OK, I want to insert a session deletion for this session, the one that has the speaker with this username and has this particular timestamp. And that session deletion has this timestamp. So now that's identifying a very specific deletion event. And now that I can specify that specific deletion event, separate from any other deletion that might have happened, now I can add my session restoration for a particular deletion. Does it also need a timestamp? That is a good question. It has to end somewhere. I choose here. And the reason is that if I restore a session and then I decide, OK, I really do need to delete it again, I can insert another deletion. And there's not additional data associated with it. So that's a really cheap duplicate insert or reinsertion. To insert a new copy of the session would be more expensive. Yes, each one refers to a single session deletion. Yes? That's a good question. What if you want a timestamp just for auditing purposes? You want to be able to see when these events happened. Then, yeah, absolutely, go ahead and add it. Just don't consider that to be part of its identity. Yeah. So that's just logging information. And also, the person that did it, that person's user ID, is also something else you might want to add to each entity. And in fact, when I do this for real, that's precisely what I do. Yeah. Yeah. Should you trust timestamps? So for the, yeah. Uh-huh. That just makes it so much easier. So only insofar as making something unique should you trust a timestamp from a client. For the purpose of keeping actual audit logs, that's when you would have a real timestamp of when that server received that message. But if you're trusting a timestamp from a client in order to, say, create a session, now you've got a speaker who's filling out these forms, creating new sessions. If the speaker is messing with the timestamps, something in the past, something in the future, duplicate timestamps, then they're still unique, except when he deliberately says this is a duplicate timestamp, and now he's really just talking about the same session. So The timestamp is just a convenient way to get something that's different every time they deliberately want to create a new session. Right. We are not ordering anything off the timestamps. They're just for uniqueness. Okay. So this is what the query starts to look like when we need to have these restorations. So we're looking for the sessions where the session ID is not in session deletion, but the session deletion is also not in the session restoration. Yeah. Yes, and that's an appropriate reaction. Although I would say go ahead and take a look at the query plan, and I think you'll be happy with the way that SQL interprets this. Yeah, right. Right, so that's an excellent observation there. If you're not updating or deleting, there are no locks. That is one of the primary motivators for starting down this path in the first place. Okay, so and even if you do end up with some problems caused by this, that would be because you've got a lot of objects that are going in, and most of them are getting deleted at some point. Then that's a place where you should rethink your model. And if you can't rethink your model, there actually is another optimization that you can put on top of this based on triggers, but we're not going to go into that one. And the DBA weeps a little more. Okay, so in summary for the deletions, a fact itself cannot be deleted. Queries that you're looking for the things that exist. Query where not exists the deletion, and if you need to restore, put a timestamp on the deletion. By the way, I'm using this term facts to represent these events that have occurred throughout time because I like to think of these as just a historical fact. And now we've got a collection of historical facts that build up and accrete over time, and then we can determine what's the current state based on looking at those facts, as opposed to using the word events. It makes more sense to me. So now, what happened to this name? Let's go ahead and take a look at that. So the name we didn't want in the speaker table, we put it in the speaker name table. Exactly. So it's got a foreign key to the speaker ID. It's got its own surrogate key. And it's got the name. And so if this was all there was to it, then how would I know what the current name is? I don't know, I just have a list of all the names that the speaker had at some point in history. What I want to do is capture a relationship among speaker names. I want to capture a partial order. So we're going to capture that as a speaker name predecessor. So that means when I've got a record in the speaker name predecessor, the predecessor is the foreign key to the older version of the name, and the successor is the foreign key to the newer version. And so now I can see this one replaced that one. Question? Mm-hmm. There's another place that you might have seen it. There's another place that you might have seen it. How many people use Git? This is how Git works. Each commit has parent commits, predecessors. Most of them have one, but some of them have two. When do you have two parents? When you do a merge. That's really what we're doing here, is we're allowing you to do branching and merging within your database. And this is now part of your data model. So let's, now if I want to uniquely identify a particular version of speaker name with stuff that's just external to the system, then I need to know the speaker. Well, here I'm highlighting the speaker ID. Really, it's the username. The value itself, and the list of predecessors. Now, how I represent those predecessors outside the system, that's a little bit interesting. But I don't know that we have enough time to get into that. Let's just talk about a specific example of a change to the speaker name. So we've got our speaker record with this particular username. And then we've got a speaker name record with my original name, Michael Perry. And then I want to change my speaker name to Michael L. Perry. If I just inserted this new speaker name record, now I can't tell which of these two came first, which one is current. So instead, in addition, I also have to insert this speaker name predecessor record that says the predecessor was Michael Perry, the successor is Michael L. Perry. So I have deliberately changed it from Michael Perry to Michael L. Perry. Now let's suppose that my system is not 100% online. Maybe I've got a copy of it. Maybe there's a copy on my laptop or on my mobile device. And so I could also change my name from Michael Perry to Mike Perry on a different device. And now what I've done is I've captured inside of these historical facts this tree. This tree has two leaves. If you have two leaves, you have a conflict. The current name might be Mike Perry, or it might be Michael L. Perry. So what you have to do, right, so let's suppose that at the time that I made this change, Mike Perry, I thought that the current name was Michael Perry. So I didn't know about this other change. So this was an offline copy of the data, a disconnected client. So now later, I recognize, hey, there's been a conflict. It could be two possible candidate names. And so I say the real name is Michael L. Perry, which points back to both candidates. And that's a merge. Exactly. So now, in order for me to know what the current name is, I have to look for all of the records that do not have successors. So the first one has two successors. They both replaced it. They've superseded it, so it's out. These other two each have a successor. It happens to be the same successor, but that's OK. They're both ruled out. This last one is the only one that has no successors, so it's the leaf of the tree. If I only have one leaf, there's no conflict. Multiple leaves, there's a conflict, and those leaves are the candidates. Yes? So could you save space by making it the successor of all the leaves in the conflict? So here we have made it. Oh, OK. So that, yeah, I think somebody answered that. It would be a mutation. It would be in a different table, but it would be a mutation of the fact itself. So the identity of the fact is all of its data and its list of predecessors. Mm-hmm. Yeah. So this does suffer the problem of the original that it accretes data and you never throw anything away. But the rate at which we accrue data, I believe, is lower than the rate at which the cost of data decreases. That's my claim. I'm not going to prove it right now, but yes. Excellent. Right, exactly. So yeah, if you were to just do a straight max, then you wouldn't be able to tell if there was a conflict. But if instead you select the name from speaker name and you look for the speaker name ID in predecessor, then you're just finding those that do not exist in the predecessor table. So that's exactly right. Yes, so if this query returns 2 rows, then you have to handle that within your application at some point. So one mechanism that I like to use is to just show that conflict to the end user. So just highlight that field, say, hey, there's been a conflict. When you hover over it, it shows you the different candidate values. And then maybe it just picks one to put in there. What's that? Yeah, they're both equally valid. Exactly. Mm-hmm. Yeah, if there was something in your domain that allowed you to say that data from this particular source is more reliable than that source, then you could just resolve that conflict automatically. But I'm not going to presume that kind of knowledge about your domain. So you get to choose what you do with this conflict. It just reveals it to you. Yes? Mm-hmm. That's an excellent question. Would you have one table per property, or would you have a single table that has all your properties and then you make predecessors of those? I lean toward that second one. So take, for example, an address. So when you change an address, you typically change all of the address. It doesn't really mean anything to change a street without changing the city, unless you've actually really just moved down the street. So same thing with name. I would group first, middle, last, maiden, all your names together, and have that be a set of properties. If you've got a whole bunch of different properties about the same person, so this is your customer database, and you know their name, and you know their address, and you know their order history, and all sorts of information about them. Each one of those groups of information, I would make a separate table. Yep. Yes? Yeah, so the advantage of this over last timestamp wins would be that that you could then choose something different to do with a conflict. You can have disconnected systems and make a change on two different systems at the same time, and then when they merge, you recognize the conflict, and then the recognition could happen everywhere. It doesn't have to be resolved as soon as the server sees the conflict. So the recognition could be just, I'm going to push all of these versions down to all the clients, and then I'm going to trust the user to be smart enough to make the right decision. And so that's very similar to Git as well, that the Git server doesn't merge our code for us. It just gives us all of the commits. And now we as a client do the merge, verify it ourselves, and then create a new commit. Yeah? Mm-hmm. Okay, excellent question. So if you need to add a new column to an existing table, then in that case, like address line 2, you could just simply make the assumption it would have been okay for the system to have had address line 2 all throughout its history, and nobody ever just put anything in it. So in that case, you go ahead and add the additional column, and all of your history just has addresses with no line 2. Okay, excellent questions. I wish I had more cards to give out. So the rules around mutable properties, they cannot be part of the entity themselves. You keep track of which versions came before as your predecessors. You query for versions that themselves have no successors, and those are your current versions. And if you have one, no conflict. If you have more than one, there's a conflict, and you have just found your candidates. And that allows you to detect and resolve conflicts, because you resolve it by having a new version that points to all your candidates. Yeah?
How does the no mutability tie into the use case right to be forgotten?
Oh, that's an excellent question. How does that tie into the right to be forgotten? This is actually one of those places where I think historical modeling is in another way, a little bit stronger than event sourcing. So with a historical model, you've got one table that represents the identity of the person who wants to be forgotten. And now everything about them has foreign keys to that table. With an event stream, it's a little bit more difficult to pick out the events that all relate to that one person. So, so it's really now just a graph problem. Identify this record, everything that points to it. If I were to try to delete this record and the database complains because there are foreign keys pointing to it, okay, those things are things that need to be deleted as well. So yeah, write to delete, that's one of those places where I would actually allow deletes in the database, and I think the structure actually helps you find the right records. Yeah. I don't know if that would be legal to just say, oh yeah, I really did forget them, if they're still there. It's a matter of trust. Yeah. So I'm not a lawyer, and I'm certainly not your lawyer, so this is the best I can do for you. Okay, so now let's talk a little bit about workflow. So we've got our session, and I want to submit my sessions to conferences. So let's create a new conference table. And this time, I'll use a GUID for the unique ID. The reason that I'm using a GUID is that when somebody creates an account with the system, they're giving you a username that they want to use. Oftentimes these days, it's an email address. And that's something coming from the domain that's already supposed to be unique. So it's a natural key. In the case of a conference, when somebody, hey, I want to create a conference, go up to your application, they don't have any other information that they're bringing to it. They're just clicking a button. And so a GUID is a really good way to do that. Timestamp would not be a good way to do that because you don't have anything else that's part of that uniqueness. So if you've got a lot of people using the system, then you're going to get conflicts on timestamp. So timestamp is good if it's already, like a session is already part of a speaker. So timestamp collisions for different speakers aren't going to be a problem. So anyway, so we've got our session and our conference. And now I want to be able to submit a session to a conference. And so I create a new submission. So it's got the session ID, the conference ID, and it itself has a timestamp. Why does it have a timestamp? Because we want to be able to delete submissions. So, oh, okay, submitted to CodeMash. Oh, wait, let me withdraw that submission. Oh, I changed my mind. I really do want to submit, so I submit it again. And I can do that multiple times because I've got those timestamps. And so now I've submitted my session to CodeMash. And now Brian, I guess it's Rob actually, who reviews the submissions and accepts which ones are going to be actually invited to speak. So he creates an acceptance. Again, it's got a timestamp because he might change his mind and withdraw that acceptance. And so all of these are different events, all of these are different facts that have occurred throughout time, and they, in their aggregate, tell me the current state of my submission. So I can see, has my submission been accepted? Just by looking for any acceptance with that foreign key. Exactly, and I have to have that where clause where not in acceptance withdrawal. Has the submission been withdrawn? I'll look for the submission withdrawal. So I can just query this structure in order to figure out the current state of the system. And I'm changing state by capturing the information that's relevant to that domain event. Yes? Good question. So what happens if you insert an acceptance, but then the speaker inserts a submission withdrawal? That's something allowed by the data model, so therefore you have to figure out what it means in your domain. The way that I would interpret that in this domain is that I would want to be able to write a query that looks for that particular scenario. Show me all of the submissions that I've accepted that the speaker has withdrawn, because now that indicates that there's work to be done. I need to contact that speaker and say, was that an accident, or should I take you off the schedule? And if I take them off the schedule, then I go ahead and withdraw the acceptance, and then I accept a different session. So by doing these queries for acceptance with no withdrawal, acceptance that have submission withdrawals, submissions with no acceptances, that gives me, in that case, show me all the submissions that haven't been withdrawn and haven't been accepted. Now I've got a queue of submissions that I need to review. So those queries give me the queues. They give me the list of things that I need to work on. And the work that I need to do in order to remove it from the queue is exactly recording a new domain event. So this is, to me, the most exciting part. So I don't have to do two things. I don't have to say, okay, remove it from the queue and accept it. Just by accepting it, it's no longer in the queue. And so the rules around workflow is that you never store status as a mutable property, not even using that mutable property pattern that we talked about. You've got domain events that move objects forward through the workflow, and they point back to the previous events that have occurred, their predecessors. You can query where the next event doesn't exist, and that gives you the queue of work that you need to do in order to create that next event. So, really powerful stuff. Now, let's talk about the architecture that this enables. We've already hinted at it a little bit. So we talked about the fact that we don't have to select and then update something. So we don't have to lock any records. We talked about how we can have offline copies of the data, make changes, and then when we get those changes put back together, we can detect and resolve conflicts. And so this opens up a lot of different architectural possibilities, occasionally connected to apps. So we've got a mobile app. It's got a subset of the data that it keeps offline. It can run these kinds of where not exist type of queries in order to show you what's current on the user interface. As you make changes, you're inserting new facts into your local copy of the database, and so that's changing the results of those queries. And that also gives you a queue of facts that you can send back to the server. And then somebody else can ask the server, hey, what other facts have you received since the last time we spoke? It sends all those back to the client. It just feathers them into its own tree and then refreshes the user interface. And now you've got fresh data. So really easy, occasionally connect to mobile apps. This also helps us with active-active clusters. So if I've got a historical model in one database and I insert into it, then I can just simply take that record that I've inserted, ship it over to the other database, and insert it there. But these can be active-active. I don't have to have the other one offline. I can have inserts happening on that one too, shipping back in the other direction. If conflicts occur, they're detected, and the application will resolve them. Yes? Excellent question. Is that part of eventual consistency? Yes, it is. So this allows a kind of eventual consistency where you choose which of these data stores you want to use. And so you'll choose the one that's closest to you. So it could be geographically. It could be that you've got an offline copy, similar to an occasionally connected mobile app, but maybe you've got a maybe you're running a restaurant and you keep an offline copy of your day's transactions where all of your point of sale systems can get access to it, but you wouldn't have to go over the network in order to, over the internet in order to get your transactions for the rest of your stores. So yeah, you've got occasionally, or you've got eventual consistency, and now you are free to choose the network topology that makes the most sense for your application, and that doesn't impact the way that you model your data. The data model already supports that. So another way that we could use this is microservices. Oftentimes we talk about microservices as REST APIs, but what if instead each one of these databases that each independent service has is a historical database? And so they are just publishing the new records that get inserted into them, and then they're subscribing to the ones that they care about for their service. And now each microservice has a subset of the data, only the parts that it cares about, and it's kept up to date by this back channel. And now the REST API is only there to serve the front end. It's only there to serve the web application or the API outside of the system. Inside, it's not using REST API calls at all in order to synchronize data. So this is another possibility that's open to you now that you can merge data by simply inserting it into a historical model. So all of this information, there's actually an example piece of code that I wrote for showing these patterns. So that's all up there on my GitHub account, michaelperry/festify. And you can also check out historicalmodeling.com for more information about this pattern and videos about how to apply it. So thank you very much.